Okay, Tro Chapter 1, Section 7. We're starting to get into some really, I think, elegant aspects of science. So we're dealing with the reliability of measurement in Section 1.7, and we're going to answer the question, what do you mean by that number? And before I do, I'm going to motivate this with just one figure that I Googled the other day. I Googled balances the other day, and this figure came up, among other things. I snapshotted it, and this figure came up. And I want to point something out here. This this apparatus to the left. Let me come over here and use my pen. This apparatus to the left is going to measure things to the. It's an analytical balance, and it's going to measure to 1, 2, 3, 4 grams to the 10,000th of a gram. Okay. This one is just a regular balance, and it's going to measure 1, 2, 3 to the milligram, right? To the thousandths of a gram. And look at the difference in price, off by a factor of roughly 10, right? So I want to point out that when we are dealing with numbers in physics and chemistry, what we mean by the numbers is very important. And as a scientist or a technician of some kind, a business person, it's going to be very expensive to get an extra digit into our numbers. Okay, so it turns out this matters very much. Even if that doesn't really resonate with you very much, perhaps you can appreciate that the numbers that we report in physics and chemistry, every digit or the absence of a digit means something. Okay, so we're going to be answering the questions: what do you mean by that number? And we're going to answer it with something called significant figures. The second question we're going to answer is, how do I use measured numbers in calculations without confusing the meaning? And then finally, since our measurements can't be perfect, how do I communicate how much meaning is in a particular measurement? All right, so there's several aspects of this section. I think I warned you at the beginning, it's an elaborate one. So let's move on. First question, what do you mean by that number, sig figs? So let's look at this. Now, if you have if you're weighing some, looks like this, I don't know if this is a walnut, I can't tell what this is, some kind of nut here, okay? If you're weighing that and you've got some apparatus that gives markings every 1 gram, then your job then as a scientist is to measure out to the tenths of a gram, or rather to estimate to the tenth of a gram. So if it's measured every 1 gram and it looks like it's about a fifth of the way between 1 and 2, about a fifth of the way to the 2, right? Can you see there's 0, there's 1, there's 2, and the person reading this says, oh, I don't know, that's about a fifth of the way, so I'm going to call that 1.2. And that's how you report this measurement right here. Well, let's look down here. Here it's measured, these markings are measured every 0.1 grams, which you really can't tell because we're not looking, at the rest of the apparatus here, but suppose it's every 0.1 grams. Can you see that this line right here goes between the 1.2 and the 1.3 hash? It's between the 1.2 and the 1.3 hash. And it turns out it's closer to the 1.3. The person reading it thinks it's about 70% of the way to the 1.3. And so he reports that as 1.27 grams, right? So that last digit is the digit of estimation, and that digit is the digit of estimation. Okay? A little better look there at that picture. Okay, so what we said before in the previous slides was that the last digit is going to be the digit of estimation. Let me go here again. That's going to be the digit of estimation, right? And these are known for certain. Okay, that's what you need to be thinking about when you're reading an analog instrument and deciding what number is the appropriate number to write. What about this one? Can you see that? Let me come back down here. I'm going to write this again. I like that. Okay. Can you see that this is more than 4.5? That's 4.5, right? This is 4, 4.1, 4.2, 4.3, 4.4, 4.5. It's more than 4.5, but less than 4.6. That is the meniscus. I guess you have to know that too. There's the bottom of this bubble that we measure. That's the top of the liquid. Okay, and that tells us how much is in there. So it's 4.5. It's more than 4.5 and less than 4.6. So the actual number is going to be 4.5 something, right? 4.5 something. And how close is that, do you suppose, to the 4.6? Oh, I think it's about, oh, I don't know, 80% of the way up. That's what I'm going to say. No, it's more like 60%. I'm going to say 4.66, okay? And that's how a scientist is going to read that number, or rather 4.56. Okay, let's do another one. Look at this here. Okay, so here's 100. Here's 101, 2, 3, 4, 5, 110. You see that? Okay, so it looks like this line is 101, 102, 103. It looks like it's between 103 and 104. I accidentally put a decimal there on accident, okay? To me, it looks like it's greater than 1.3 and less than 1.4. So I'm going to say, I don't know, that's a little bit past the middle of that line right there. I'm going to say it's 103.1. Okay? Now, another scientist might come up and read that as 103.0 or 103.2. But these numbers are all the same number. 103.0 and 103.2 are all the same number, right? Because that last digit is the digit of uncertainty. And we all agree that it's 103 point something. All right, so let's talk about significant figure rules. Those are the previous slides were dedicated to how you report a number that you're trying to communicate. How do you read someone else's number? How many significant figures are in these following numbers, okay? So first sig fig rule is all non-zero digits are significant. Okay, so if you have the number 28.03, can you see that these three are non-zero digits? So there's at least 3 sig figs in there, right? And here there are 2 non-zeros. There's at least 2. All non-zero digits are significant. Okay, the next rule is interior zeros. That is, zeros between other significant figures are significant. So here's a 0 that's between 2 non-zeros, right? So that's significant, and there's a 0 that's significant because of this rule, right? That 4 is significant because of the first rule. Okay? That 3 is significant because of the first rule. That 0 is significant because of the second rule. Okay? So it looks like there's 5 sig figs there in that number. Okay, the third rule is leading zeros, that is, zeros to the left of the first non-zero digit, are not significant. Right? So we look to the first non-zero digit, which is the 3 here, and everything to the left of that is insignificant. They only serve to locate the decimal point. They basically tell how big or small a number that is. Same here, 6. Everything to the left of that, all the zeros to the left of the first non-zero digit are insignificant because they're only telling how far away they are from the decimal point. Okay, what about trailing zeros? Zeros at the end of a number are categorized as follows. Trailing zeros after decimal point are always significant, right? Because they mean that's how much confidence we have in the number. That's what they mean. So those 3 are all significant, and these 2 are significant because they're after the decimal point. Trailing zeros are zeros after the decimal. They're trailing other significant figures, and they're after the decimal point. Okay, trailing zeros before a decimal point and after a non-zero number are always significant. Okay, so here's a decimal point, there's a trailing 0, but there's a decimal point in there, and there's some afterwards, therefore that's significant. Okay, trailing zeros before an implied decimal point are ambiguous, and they should be avoided by using scientific notation. I mean, look, if you Google this, you're going to come across some very helpful resources, but they're not always super consistent on this. Trailing zeros before an implied decimal point. So this says it's ambiguous. Most people would say that that's a trailing 0, but it only shows how far it is away from the decimal point. Therefore, it's not significant. All right. So if you want to say 1200, and because of the way that you gathered your information, depending on the scale that you used or the apparatus that you used to measure, you want to indicate you've got 2 sig figs in your 1200, then you write it like this. If you want to indicate you've got 3 sig figs in this number, 1200, you write it like this, 1.20 times 10 to the 3. Can you see I've got a trailing 0 now? That makes it significant according to rule number 4.A, right? And then if you've got 4 sig figs, you write it like that. Okay? And some textbooks will put a decimal point after one or more trailing zeros. If the zeros are going to be considered significant, in other words, you want 4 sig figs, you might write it like that. Tro says he avoids it in this textbook. You should be aware of it. Occasionally it shows up in some problem sets. So, you know, if it shows up in problem sets in our class, I'm gonna assume you're gonna be okay with it. I don't like it, but neither do I work too hard to shield students from it. Okay, so measurements. It's important to appreciate that sometimes when we measure, we use instruments that have limited accuracy, but we need to communicate the limitations. We use sig figs, but sometimes we measure by counting, and in counting there's no uncertainty. We know things that we count. We know with unlimited precision, and we call these numbers to be exact. All right. So let's go back one second here. For example, if I was counting people, and I said there were, 10 people in a particular room. There's exactly 10 people. We would know there's not 10.001 people. There's not 9.9999999 people. There's exactly 10. And that's a number that we call exact. And so we would say it has an unlimited number of significant figures. And we'll see how that's important when we're doing calculations. Okay, so the second question we're going to answer is, how do we use measured numbers in calculations without losing the meaning? So let's talk about doing calculations with measurements. So rules for calculations. In multiplication or division, the result carries the same number of significant figures as the factor with the fewest sig figs, okay? So look at this here now. In multiplication or division, the result carries the same number as the sig figs as the factor with the fewest sig figs. So an example, you got here 1.052, that's got 4 sig figs in it, that's got 5 sig figs in it, it's got 2 sig figs in it. So this number is going to have 2 sig figs in it. We can multiply all those with a calculator, but then when we go to report it, we've got to say 6.7. All right, can you see that? Because the fewest sig figs is with that factor, therefore this can only have 2 sig figs. Okay, what about this one? This one's got 5 sig figs in it. This has got 3 sig figs in it because that's a trailing 0, right? So this number's going to have 3 sig figs in it. This is going to be reported as 0.626. Okay. Now, in addition or subtraction, the result carries the same number of decimal places as the quantity with the fewest decimal places. All right, this will make some sense after we look at it. Okay, so if we're adding these numbers, we line all the decimal points up, all right? Then we add the numbers all up, and then we say, aha, that's the number right there with the fewest decimal places, 0.07. And so we can only report this to 5.41. Okay, when rounding to the correct number of sig figs, round down if the last or leftmost digit drops is 4 or less, round up if it's 5 or more. To 2 sig figs, round, this was going to round to what? This is going to round to 5.4, right? To 2 sig figs, this is going to round to 5.3. To 2 sig figs, this rounds to 5.4, right? Because that digit right there is getting dropped, but it's 5 or better. This is going to round to 5.3 because that digit is getting dropped too. Because that digit is getting dropped and it's 4. Okay? To avoid rounding errors in multi-step calculations, round only the final answer. Tro doesn't do this in this text because it's really complicated. He says in the beginning of the text he doesn't do it. But when I'm doing problems in class or somehow with you personally, I'll try to be consistent with this. In order to be absolutely certain, this is what you must follow. I would say if you break this rule, oftentimes you get the right answer anyway. To avoid rounding errors in multi-step calculations, round only the final answer. Do not round the intermediate steps. If you write down the intermediate steps, keep track of sig figs by underlining the least sig digit. Okay? So let me give you an example of what he would mean by that. 5.7, right? So suppose this is the problem that we're given. Once we get this, 5.489 minus 5.01, here's where we do this. 5.489 minus 5.001, right? Those get dropped. Let's subtract these out. That goes to 1. That goes to 1. That goes to 4. Got an extra digit in there, right? Wait. 9. I'm sorry. This is supposed to be a subtraction problem. No, this is a mistake. It's not a 1. 9 minus 0 is 9, right? 8 minus 0 is 8. You're probably thinking, what is this guy doing? All right, let's just get rid of that line. 9 minus 0 is 9. 8 minus 0 is 8. 4 minus 0 is 4. Man. Okay, to avoid rounding errors in multi-step calculations, To avoid rounding errors in multi-step calculations, round only the final answer. Do not round intermediate steps. If you write down intermediate steps, keep track of sig figs by underlining the least significant figure. Okay, in other words, don't even obey any of these rules until you get down to the end. And then you're gonna, if you've got a complicated calculation, you're gonna have to track it, right? So let's look at an example. 6.78 times 5.903 times the difference of these, right? Well, the first thing I'm going to do is what's in the parentheses, okay? So let's go over here, 5.489, 5.01, okay. 9 minus 0 is 9, 8 minus 1 is 7, 4 minus 0 is 4. Okay, so it's 0.479. But we know that, okay, that was the last sig fig. Right? So there's only really, we use 0.479, but there's really only 2 sig figs in this number, right? Because of that subtraction problem. 2 sig figs. That's scary. 2 sig figs. But now that we do that, we multiply this number times that number times that number. We underline the 7 to remind ourselves it's really 2 sig figs. And so when we get our final calculation, we take it down to 2 sig figs, 19. Okay, hope that's helpful. Look at this problem, and I'm going to give you a minute to do that problem. I'm going to do it myself. So pause the video right now and do this problem, and then see if it's consistent with mine. Okay, so I'm going to suppose you paused it, and I'm going to come over here, and I'm going to do it. Oops, just a minute here. I'm going to suppose that you've paused it. 452.6755, 452.33. It's a subtraction problem. That's 5 and that's 5. That's 4. Okay, so how many sig figs are in this number right here? Well, don't forget that we had to round off there, right? So this number is 0.3455, but that's the last sig fig. So there are 2 sig figs in this number. Okay, now we're going to take 4.562 times, I'm doing this in a calculator, I'm not doing this in my head, 3.99870 times 0.3455 455, and we're going to get, when I multiply all these numbers out, 6.3026349, and so on. Okay, but how many sig figs do I have in the final answer? Well, this number, right, it's a multiplication and division problem, multiplication and division. This number's got 4 sig figs in it. This number's got 1, 2, 3, 4, 5, 6 sig figs in it. And what's this number got in it? 2, right? Because the math problem I did right here, the addition and subtraction problem. So this then is going to have to be reported to 2 sig figs because it's a multiplication and division problem. 6.3. Okay, hope that's helpful. Now, let's go on to the next problem. Reporting to the correct number of sig figs. The graduated cylinder shown in the figure below report the volume. Has markings every 0.1 meters. You know what? We did this in a previous question, right? So let's come over here. Pen. It looks like it's more than 4.5, less than 4.6. If I'm looking at the middle of each of those, I think it's about, I'm going to say 60% of the way up. I'm going to say 4.56 mils. Okay, let's do another one. The thermometer. You look at that one. Again, I'm going to say 103.1. Okay, so let's do an example now of determining the number of sig figs in a number. So let's look at these. Now, what I did for this video is I pasted the rules over from a previous page. What was that page? I pasted the rules over here from page, what's the rules for sig figs? From page 21. Here's the rules from page 21, and let's look at each of these in light of these rules, okay? So first of all, look at, I got those 3 I know for sure according to the first rule because those are all non-zero. So there's at least 3 right there, right? But then I've got interior zeros, that's zeros between non-zeros, and there's none there. Right? Can you see there's a non-zero, and a non-zero? There's no interiors. Okay? So let me get a red pen here. So 0.04450. Alright, there's a non-zero, there's a non-zero, and there's a non-zero. So I've got at least 3. According to rule number 1, I've got at least 3. Now, there's no interior zeros. What about leading zeros? There's zeros to the left of the first non-zero digit. Here's the first non-zero digit. Zeros to the left of it are here. They're not significant. They only locate the decimal point, okay? So those are not. What about trailing zeros? Trailing zeros after decimal point are always significant. And here's the decimal point over here, right? So that's definitely significant. There you go, according to rule number 4A. All right, so there's 4 sig figs here in this first one. What about the next one? 5.0003. All right, here's a non-zero, and here's a non-zero. So according to this rule number 1, there's at least 2 here. All right, and number 2 rule, interior zeros. That is zeros between 2 digits. Boom. 3. All 3 of those are. So there's 5 sig figs here. What about C? 10 decimeters is equal to 1 meters. Aha! These are counting. These are definitions. So there's an unlimited number of sig figs here. Unlimited, because this is a definition, right? There's exactly 10 for exactly 1. Since this is exact and this is exact, we would say that there's an infinite number of sig figs in both sides here, right? Look at that. Okay. What about 1.000 times 10 to the 5 seconds? All right, so we know that first one is, because that's a non-zero digit, right? That's significant. Interior zeros, there are no interior zeros. What about leading zeros? That's zeros to the left. There's none there. What about trailing zeros? Aha. They are trailing zeros after decimal point are always significant. So it looks like all three of those are. Therefore, there's 4 sig figs there. Okay, I'm going to leave the last 2 for you to do on your own. The next, for practice example 1.5, is more practice problems. I'm going to let you do those on your own. I still pasted the rules here from page 21. I still pasted them here, but why don't you do those? You should do those on your own. And we'll discuss the answers in class if you've got questions about those. Okay? All right, so finally, sig figs and calculations. Yeah, example 1.6. Well, we've done a couple of these examples, but let's do another one. Let's do A and B, and then we'll be done. So A and B, and then we'll leave the rest for you. 1.0, 5.51, 4.0 divided by that. All right, so this is all a division multiplication problem. So I'm going to go through here and say how many sig figs are in each one. There's 3 in this one. There's 4 in this one. There's 5 in this one. And there's 5. There are 5, pardon my grammar, 5 sig figs in that one. So the answer is going to have how many sig figs? It's going to have 3 sig figs in it. All right, so what I'm going to do is go to my calculator. I'm going to say 1.10 times 0.5120 times 4.0015 divided by 3.4555, and I'm going to get roughly 0.6521 and so on. And it looks like I've got 3 sig figs here, so that's going to round down to 0.652. 0.652 is the answer there. All right, what about this one? Okay, so it looks like we're going to end up, we've already lined up the decimal point, or the author has lined this up for us. So I'm going to say 0.355. 0.355 plus 105.1 minus 100.5820, and it gives me 4.8730. Can you read that? It's 4.8730, but it lines up to that point right there, right? So this is going to have to be reported as 4.9. All right. Okay, so let's move on to the last section of this section. And we have to finally answer, since our measurements can be perfect, how do I communicate how much meaning is in the measurement? And this pertains to certainty, as we might describe by accuracy and precision. So first of all, accuracy is how close the measured value is to the actual value. And what is that? Well, it's difficult to appreciate without an example. What is the actual value? Let's figure that out by examples. Precision, how close a series of measurements are to each other. All right. So keeping those two definitions in mind, which I posted here at the bottom of the page, look at these sets of measurements. So suppose student A takes a bunch of measurements and some mass, obviously, and finds out student A finds masses of 10.49, 9.79, 9.92, and 10.31. Okay, the average is 10.13. And look at those numbers. How close are they to 10.13? So the first question I'm going to ask is, are they accurate? The next question is I'm going to ask, are they precise? Oops, let's go back here. Are they precise? Well, we don't know what the actual value is, right? This is not the actual value. That's just the average. Student B, they might be a really very, very smart student. And student A says, oh yeah, student A's, or rather student B is so smart, they must be right. That's going to be the actual value. Well, no, this is still just a scientist measuring things, right? Student C, same thing. So let's look at these. Tell me, are these numbers close to each other for precision? How close are, because so again, we can't say much about accuracy here, but we can say something about the precision. Are these guys close to each other? And I would say, 9.79, rounds to 10. That rounds to 10. These all round to 10. But if you compare them to these numbers over here, these are much closer to each other. Can you see that? These all round to 9.8. And shoot, these are even more precise yet, right? Can you see that? These are close to each other. These numbers are close to each other. These two numbers are not actually that close to each other, right? So if this was an actual experiment, we might say to student B and student C, you've got something going on here because your measurements are all pretty precise, but they're not close to each other. But I should say these two students' numbers are not close to each other. These numbers are all close to each other, and these numbers are all close to each other. So I would say these are precise, and these are precise. Sorry. And these yet are not precise. Okay, now let's go on to a better example. So, or rather a more elaborate representation of those numbers. Suppose we knew that the true mass, and you'd have to be told this by looking in a book somewhere. Suppose you know that the true mass was 10. If you knew the true mass was 10, you would go, wow, these numbers are wildly divergent, right? So they're not only not very precise, but their average comes to 10.13, and if the true number is 10, right, you go, wow, that's not very accurate either. Now these numbers are all very close to each other, but they're not that close to 10. So since they're not close to the actual value, which is something we looked up in a book or someone told us, then we would say they're precise but not accurate. Okay? I'm going to say these are not accurate. These are not precise. These are not accurate, but they are precise. Okay, now look at these numbers. They're all very close to each other and very close to the actual value. So we're going to say they're accurate and they're precise. Can you read my writing? Okay. So a couple sort of an example here about the terms accuracy and precision. Let me go back to it. Accuracy shows how close the measured value is to the actual value, and we can't determine accuracy unless we're given an actual value, either in a question stem or we look it up in a book, see it in a table. But precision you can always tell because you can look and see how close a series of measurements are to each other.